Starting the stream. Let's see if I can hear myself. Starting the stream. Okay. This does work. Let's see if I can hear myself. Starting the stream. Okay. This does work. Let's see if I can hear myself. Starting the stream. Okay. This does work. Let's see if I can hear myself. Starting the stream. Okay. This does work. Let's see if I can hear myself. Starting the stream. Okay. This does work. Okay, now it fits perfectly. Alright, so for the stream today, I'm going to go over a bunch of questions I missed in the Quiz Bowl tournament today, which I competed in with a bunch of other dudes from my team. I competed in the Rainstein varsity competition with my school, and we did alright. I did pretty badly, and I think I did pretty badly because, number one, I was not really used to the style, because it was sort of different from the competition I was competing in previously. Previously we had 5 people. There were no negs when you buzzed early if you got it wrong, but now there's 4 people and there's negs. And then we also didn't have our best team and the people that I knew the best, although we had most of our core members. The other thing was that the questions were just considerably harder for this round than for all the other tournaments, which I think is a good thing, because exposure to difficult things, well, number one, humbles you, makes you think, oh wow, I'm really stupid. Makes you realize, oh wow, there's so much stuff I don't know that's actually relevant to the human civilization. And then also it just makes you better at easy level things. It's like, it's like once you're using artillery, right, intercontinental missiles, you're gonna know how to probably fight like a normal war. Okay, that's a bad analogy. It's like using a missile to hit like an insect or that kind of stuff. If you didn't get my analogy, that's totally fine. But we are going to go over some content. So let's do round 1. So, respectively, R2, R3, R4, R5, R6, R7, and R8. So I can also pull up my stats. Actually, I remember. So my PP for 20 absurd was around I think it was 16 point something, which is 16.4 or something like that, which is pretty bad. I had 2 powers. I had 13 toss-ups and 8 negs, so a total of 30 plus 130 minus 40, which is 120 points. Which was pretty bad, you know, but it is what it is. Okay, so let's go over what I missed from round one. So from round one, I missed, there's this one question on oxygen. So I can't remember all the clues from the question, but the part where I wanted to buzz was like organisms that that can't use this material are unable to go into or they're unable to do glycolysis properly. So I mean they have to do anaerobic respiration, which at that point it was sort of like a giveaway, but I said glucose for some reason, and it also like stayed on the buzzer for like several seconds, not knowing what to do. So I mean clearly my subconscious had already known that the answer was oxygen. And prompted me to buzz, but for some reason I just couldn't, like, in my brain recall what the answer is and communicate it. So, I mean, just as, like, a brief explanation here. What happens in glycolysis is you have glucose, right? So C6H12. O6. And then what happens is a bunch of stuff happens, and you get you lose 2 carbon molecules in the form of carbon dioxide. You get a bunch of NADH, which is a really strong ion that gets to produce a bunch of ATP. I think it's NADH plus, or no, it's NAD plus. So I think you get 2 of that, and then you end up with 2 cyclic AMPs. Oh no, you end up with 2 acetyl-CoAs. All right, so CoA. You know what? I should probably just type this, since drawing this with my mouse is just torture. Okay. So this is glycolysis. And this is what we do. I mean, after this, what happens is you jump through that, and then you run into the Krebs cycle, which bumps you up, which bumps up the NAD count and generates a bunch of ATP. Yeah, so you also get 2 ATP here. And then you get a bunch of ATP. I think it's like 4 ATP or something. And you get a bunch of, I think you get 3 NAD plus and 2 FADH plus, or FAD plus. And an FAD is just like a weaker version of an NAD. This is like the Krebs cycle. Okay, glycolysis. Which starts with 2 acetyl-CoA, and then I think you run the cycle twice for each acetyl-CoA. And then there's the ETC, the electron transport chain, where we're using a sort of interesting mechanism that's coupled with the sodium-potassium pump. You use like almost like a fishing method. So you like pump out the NAD, or the NAD, since it gets a hydrogen, which is part of water, so it somehow acquires a random hydrogen, and then as a result it releases an electron, and the electron goes through this chain of stuff, this chain of motion, and then captures a bunch of ATP. So that's the idea behind this. But for organisms that can't breathe in oxygen regularly, since you need like a lot of oxygen to do all of this, right? If you can't get enough oxygen, then you can only do like a watered down version of glycolysis, which is called fermentation. So or anaerobic respiration. So you can either like ferment like yeast and that kind of stuff. So it's like in bread, or you can ferment milk, and that's how you get like yogurt and other stuff. So I think that was the clue for oxygen. The answer was oxygen. Now, alternatively, I sort of want to check out the clues for oxygen to just get a better understanding. So I'm going to look up the Wikipedia for oxygen. Let's see what it says. Oxygen. Gas. Okay. Number 8. Chalcogen. So I'm assuming, yeah, that's the group. So it's before halogens and after pnictogens. Group 15 table. Okay, so back to oxygen. It's a chalcogen group on the periodic table. A highly reactive nonmetal. Actually, I'm gonna turn on the lights here. Oxidizing agent. Earth's most abundant element after hydrogen and helium. Third most abundant in the universe, also after those two. Standard. Yeah, I think abundance, just as like a side note, yeah, in the universe, it's hydrogen, helium, oxygen, carbon, neon, iron, nitrogen, silicon. Well, okay, so these 4 are very common because of nuclear fusion that happens inside stars. You start with hydrogen and helium, which are in the form of nebula, and then they eventually form stars. Stars are very hot. It's like a big furnace inside, and then so you compress like a bunch of ionized hydrogen and helium, and then their nucleuses just pile up together to become heavier elements. But the upper limit, the upper cap for stars, for fusion formation is iron. Yeah. Yeah, but only 4.6% of the universe's energy comprises of the visible baryonic matter. And a baryon is just like stuff that is made up from quarks, like okay, that's another rabbit hole. What's a baryon? Yeah, well, just particles that have 3 quarks. Like protons and neutrons. And then you have exotic baryons, like pentaquarks. Okay, members. Residual strong force, yeah, mesons. So, and more generally, they are hadrons. So, hadrons contain, okay, before we jump too far down into the rabbit hole, let me make some notes. Okay. So baryon is a class of particles, and 2 hadrons. Hadron is basically a composition of quarks. There's the triquark, which is more common for, like, say, protons and neutrons. And there's also the exotic baryon, which is pentaquarks. So what's special about the baryon is that, classification, it is a type of hadron. Yeah. So I should say it's not related to hadrons, it's a type of hadron. So what it looks like using the diagram is you've got bosons, you've got fermions, and you've got hadrons. So here you've got baryons here, and you've got mesons here. These are bosons, which are force-carrying particles, and these are fermions, which are, okay, bosons have integer spin, fermions have half-integer spin, and these are hadrons. Okay, so exotic baryons might not actually exist. However, the LHCb CP violation in the interactions of B hadrons. Oh yeah, I also missed a question, or I lost on the buzzer, or a question on the weak force, which I should have gotten it based off of line 1, but I didn't. CB experiment observed 2 resonances. And no idea what that is. Combined statistical significance of 15 sigma. That means they sort of had, like, some empirical evidence of its existence. And yeah, so I mean, so long as your spin adds up to 1, so you can also have, like, weird types of quarks, like heptaquarks or nonaquarks. So, I mean, hepta means 7, nona means 9, right? Like a heptagon is, right, a heptagon or a 7-gon, and a nonagon is like a 9-gon. Yeah, because hepta and nona is from Greek, right? While most of our naming system is actually Latin. Yeah, hepta is Greek. Like dodecagon is also Greek. Okay. So baryon matter is basically all matter that is made from baryons, and it's basically what we're made of. Most of the stuff we see is made of. Most of the stuff we interact with is made from that. But surprisingly or unsurprisingly, that is only 4.6% of the energy in our universe, according to physicists. Baryons came to outnumber their antiparticles, baryonogenesis. Okay. So So naming. There's also and Nona quarks. Just gonna add that to the dictionary. So this, an exotic baryon would be 4 plus 1, or 5 plus 2, 6 plus 3. For pentaquarks, the LHCb experiment in 2015 provided some empirical evidence of its existence. LHCb experiment at CERN on B physics. Right? Am I getting this right? Designed to, yeah, okay, so measure parameters of CP violation. Measure CP violation. And CP violation is by Chening Yang and Zhengdao Li, 1956, I think. Oh, whoops. Wrong browser. Okay, nope. Could have been 1953. Or 1952. Or 1951. Or 1954. Or 1955. Or 1957. Ah, here. Cengdao Li and Chening Yang. So it was about CP violation. Okay, so it is 4.6% of the universe. Non-baryonic matter consists of black holes, neutrinos, electrons, or just leptons in general. And their antimatter. What else? Okay, supersymmetric particles. Okay, dark matter. Dark matter is not baryonic matter for obvious reasons. Supersymmetry. Axions and black holes. Okay. Dark matter. Okay, by the way, I'm gonna, yeah. Okay, baryogenesis. Okay, so there's this idea called baryogenesis, which, so people think that the amount of baryons should be conserved. That is, you should have like the same number of baryons as well as their antiparticles. That should like add up to like a certain number or 0. But this is actually not conserved. And so it's not conserved for reasons people aren't really sure yet, but it has to do with like some initial state of the universe in the Big Bang Theory. Granted, protons may also hypothetically decay, but people don't really know about that. So due to the amount of baryons should be conserved in the universe, but it's not for some reason. Okay. Alright, so due to the action of splarons, what are splarons? Okay, some weird thing. Alright, so violation 2, standard model, grand unified theories. Oh my goodness, the gut. Okay, so the gut predicts that a single proton can decay, but this is like crazy stuff because this is almost always or almost never verifiable. All right, so okay. All right, the gut some grand unified theories suggest protons can decay, thus changing the number, but there's no evidence. Okay. Yeah. There's the non-conservation of baryon number in the very early universe. Also, changing multiples of 3 due to the actions of Spherion. What's a Spherion? Okay, actually, oh, Greek for slippery. Standard model. Derivative methods. Saddle point of the electroweak potential. Okay. Spherion, roughly high energy composite of 3 electrons or of 3 baryons. Okay. I can't really understand the math involved for this yet, so I'm usually just going to skip the math part, since also for Quizable preparation, they're not going to actually, like, name the formula for stuff. Oh, Max Tegmark. Oh, I know who he is. Conversion of baryons to antileptons would be orders of magnitude higher than the efficiency generation, such as nuclear fusion. An extremely advanced civilization might use spheralizer to generate energy from ordinary baryonic matter. Okay, that is very sci-fi. Okay, Flareons. I sort of get what they are. Perturbation methods. Okay. Just a quick definition. Perturbation theory. Okay. So, explaining what Flareons are. So Flareons are saddle points to the electroweak equation. So like a saddle point is like a point that is like on like a saddle. So like this point over here. Granted, my drawing is really bad, so you're just going to have to bear with me. You can always look at the Wikipedia diagram. Okay, so it's a saddle point to the electroweak equation, which is probably important, so I'm going to highlight that. What is it? It is non-perturbative, which means it can't be bashed by Taylor series. Okay. Use either composed of 3 baryons or 3 leptons, thus violating the baryon and lepton number. Oh yeah, by the way, this is... Okay. Okay, it's a saddle point to the electroweak potential and a solution, or a static solution, to the electroweak field equation. Which static solution means it's like time independent. However, B minus L is conserved because it's always this makes sense because you either take 3 baryons or 3 leptons, and you probably like take the same amount from each. So their difference is always conserved under this scheme, which means you have the same amount of Flareons that are made from baryons or leptons. Did I spell that right? It's S-P-H-A-L-E-R-O. Yep, okay. And then, so, has energy around 10 mega electron volts? Oh no, 10 TeV, TeV electron volts. But can't be produced in LHC because no way to render the energy in a combined fashion. That makes me wonder, like, how much energy can the LHC generate? I'm just gonna check that out. LHC is very big. LHCb, which we talked about earlier, because in empirical data for pentaquarks, which is like a type of exotic baryon, is in there. Okay, so their maximum is 6.8 tevatrons per term, or per beam. That means LHC maximum is 6.8 per beam. Teva electron volts per beam, or 13.6 per batch. Per collision. Yeah. And yeah, so 13.6 is double 6.8. I mean, the collision energy, since energy is conserved for these particles, it's just for each beam, how it works is like the particles just swoosh around inside the LHC and they bang up together. So that's why the combined energy is twice the amount for each beam. Okay. It's flaring on. Okay, so very rare. Is this completely hypothetical? Yeah, okay, it is hypothetical. Okay. Yeah, alright. This is important. And very uncommon. Okay, so this is a Flareon. Now, with the link to that page, let me link to that page. So, could be due Flareons. Okay, I'm gonna hyperlink that. Non-conservation. Okay. So let's go back to baryons now that we've jumped through that rabbit hole. Oh, here we go. Baryons. Also don't know what supersymmetry is. This looks incredibly complicated. I'm just gonna read like the headline. There's an existent symmetry between particles with integer spin and particles with half integer spin. Yeah, bosons have integer spin, fermions have half integer spin. Okay. Sussy. Okay, that's very sussy. Dozens of supersymmetric theories exist. Supersymmetry is a type of space-time symmetry. Okay. Bose-Einstein statistics. This actually sounds very familiar. And Fermi-Dirac statistics. Oh yeah, there's a lot of stuff named after Paul Dirac. There was a question on Paul Dirac today, and there's a lot of weird stuff. Okay. Selectron, a super partner electron, boson partner of the okay. Super partners, internal quantum numbers besides spin, spontaneously broken symmetry. Okay, so there's a plethora of similar theories on this, which suggests that every particle has like a counterpart to it. It's completely theoretical or hypothetical, so there's really no verification to that. But it's a type of space-time symmetry. Okay. Spontaneously broken symmetry. Okay. Here's the physics, quantum mechanics, distal mechanics. Supersymmetric extension of the standard model, physics beyond the standard model. BSM. This would probably be useful for general learning. I'm not sure if this will be relevant to Quizlet at all. But since I do plan on like going into physics, this would be helpful for later things. Okay, what are axions? Axions are hypothetical particles. Pesce-Quinn theory. Strong CP problem. Why does QCD preserve CP symmetry? I thought CP symmetry... Oh, well, okay. That's interesting. Charge, conjunction, and parity. Electronic dipole moment. It's like electric dance music. Naturalness problem for the standard model. Why should this parameter, or why should QCD? Okay, so this has to do with the strong CP problem, which, so CP in essence is, so C is charge conjugation and P is parity. So what charge conjugation is I think it's like the conservation of charge, right? Actually, I'm right about that. Yeah, okay, so charge conjugation is just the idea to flip charges and keep all the rest of the stuff same, and things should behave similarly. Because, like, I mean, you would expect, like, things with positive charge and things with negative charge to behave sort of similarly. That's the idea. What parity is sort of like flipping something over, like across a mirror. Like, would that violate the laws of physics, or would it conserve the laws of physics? So usually parity is conserved. That means that I should, like, for example, like a physical behavior or phenomenon should have like the same behavior in my world and in the reflected world, because I mean that's what you should expect. So there's also CPT symmetry, so there's also like T symmetry or time reversal, which means like basically the laws of physics is preserved across multiple times on the timeline, or just at like another timestamp. So yeah, they govern electromagnetism, gravity, and strong and weak interactions. Okay, but yeah. Okay, Qin or Wu Qinsheng demonstrated that the weak interaction violated P symmetry. Okay. CP violation. Oh, okay, so James Cronin and Val Fitch discovered CP violation, whereas Chen Yingyang proposed P violation. Okay, P violation under weak interaction. It's by Chen Yingyang and Sungdao Li. Just talk about CP violation. So, Xiong Wu or Wu Jianqiong demonstrated in 1987 that parity is not conserved under weak interaction, which was proposed by Yang and Lee. I've heard people say that Qin Xiong Wu should actually get a Nobel Prize as well. But apparently they didn't. I think it also had to do with her sex, since she was a female at the time, and they were sort of discriminated upon, especially in the realm of theoretical physics. Granted, she was an experimental physicist. So, CP symmetry. Discovery of CP in 1964. Decay of natural kaons. Okay, another weird particle. I resulted in the Nobel Prize in Physics. Okay, James Cronin and Val Lodgson Finch. So V.L. Fitch. Okay, so CP violation. 1980 Nobel Physics Award for what are their names? Cronin. And Val Fitch. Okay. Then so C stands for charge, conjugation, flipping charges. P stands for parity, switch flipping. T stands for time reversal, changing time. So there's also something called CPT symmetry, which is usually the basis for a lot of the physics stuff that we understand. Like, I think it's like the basis for relativity or something like that. But yeah, this is like physics beyond the model. But for axions, there's also this thing called the QCD. Wait, what is it called again? Okay, yeah, and all this started out with oxygen. Great. C symmetry. Oh yeah, the strong CP problem. So historically, Feynman and a bunch of other dudes in the 50s developed QCD. Oh no, Feynman developed QED, sorry. Okay, so QCD is quantum chromodynamics. And so the special thing about it is that it has very small parameter for CP violation, almost 0. The question is, why is this? Okay. Is this theta? This looks like theta. Yeah, well, I mean, it's between 0 and 2 pi, so it's probably an angle of some sort. It's probably theta. Currently unobserved EDM implies CP violation. Okay. Prediction. Postulated more elegant solutions of strong CP problem. The Pesce-Quinn mechanism. Effectively promote to a field. Global symmetry. Okay. Spontaneously broken. A new particle. Shown independently by Frank Wilczek and Steven Weinberg. I do know who Steven Weinberg is. That fills the role of theta, naturally relaxing the CP violation parameter to 0. Particle axon after a brand of laundry detergent because it cleaned up a problem. That's funny. The Higlet. Non-zero mass. It's a pseudo Nambu Goldstone boson. Oh my goodness. You know, sometimes I wonder, like, is any of this real? Is any of this by any means meaningful at all? Because, like, I don't know, it's like, you see this kind of stuff and you feel effed, low-key. Okay, so, yeah, I can't memorize all of this. The only thing I can do is related to particle proposed by Pesce and Quinn to solve the strong CP problem. They changed the CP violation parameter theta in the standard model into a field, and they added a new type of symmetry called the Pesce-Quinn global symmetry, which was broken. Resulting in a new particle called the axion, named after it was verified independently by Frank and Steven Berg. Wilczek. Okay. Alright, so this could also have something to do with axons. Wait, where did I hear it? Okay. Could. Yeah, I think it goes back to baryons, right? Wait, what the heck? Oh, okay, yeah. Okay, no. So, supersymmetric particles. Particles are really complicated. Then axons. Just copy a link to that. Insert length. Insert link. Okay, isospin and charge. it's a permutation. Okay, wait. What is an isospin? Respectively. I don't get why a triple U is. Okay, I think because like an up quark, so like 3 up quarks correspond to positive 3/2. 1 up quark is positive 1/2, or 2 up quarks. 1 up quark is negative 1/2, and 3 down quarks is negative 3/2. Yeah, don't really get that. Okay, number of ups and down quarks, antiquarks. I mean, that sort of makes sense since this is probably like the difference between the number of up quarks and down quarks. Okay. Oh, this is the properties of a baryon. Strangeness flavored quantum number. Oh my goodness. Okay. And parity. Nucleon delta lambda sigma xi omega particle delta group. Okay, I'm gonna stop at isospin. Okay. And charge. Quantum number. Spin. And parity. And then divided into 6 groups. Right. Okay, Ns are baryons. Oh, okay, this is entirely dependent on isospin. Okay. And subscripts indicate any heavy quark content. In case strongly had their masses as part of their names. Delta plus plus 1, 2, 3, 2. Okay, so an N is when there's 2 of one kind and 1 of the other kind, and a delta is when there's 3 of a kind. Okay. Yeah. Lambda baryons or sigma baryons. Third quark is heavy. It's given by a subscript. What is a heavy quark? Okay, heavy quark effective theory is an effective field theory describing the physics of heavy. Okay, heavy quark effective theory. Hadrons containing a charm or a bottom quark. Okay. So, I mean, just as like a quick summary, I mean, for the standard model, that's what you have. At least I know my standard model pretty well, I hope. So, first of all, there's the Higgs boson, the big H, that gives everything mass. It's like the God particle. And then you have bosons and here. And fermions. So bosons are the force particles, and fermions are the other like mass particles and that kind of stuff. So quarks, there's up, down, top, or strange, charm, and top, bottom, or bottom, right? Yep, okay. And then you have electron, you have the electron neutrino, you have the tauon, T neutrino, and you have the, oh, the muon, wait. So there's also the M neutrino. And then so what happens here is this is Gen 1, Gen 2, and Gen 3. So Gen 1s are the most common, Gen 2s are less common, and Gen 3s are very uncommon. These two are heavy quarks. Okay, these are on. What is this about? This is the standard model. Alright, for bosons you have the photon, you have the gluon. So the photon is for E and M force. The gluon, which is for the strong force, you have the W boson and the D boson. And together they are in charge of the weak force. Let me have a look. Oh, it's the W boson and the Z boson. Okay. Anyway, divided into 6 groups. So they are delta if they have 3 of a kind in up or down quarks. N if they are 1 to 2 in U or D quarks. They are lambda if they contain 2 U or D and or D quarks. They are lambda if I is 0 or sigma if I is 1 with subscript 0 if they contain heavy quark, charm bottom. If they, okay, contain 1U or D quark, they are C with blah blah blah. And if they contain no U or D, they are C or delta N lambda sigma C, and what else? Oh, and omega. Okay. Oh yeah, isospin is I. I'm just gonna add a page called isospin. Isospin is basically equal to 1/2 number of U quarks, number of D quarks, at minus number of anti-U quarks minus number of anti-D quarks. Okay. Oh no, okay, so it's... Actually, yeah, no. That was also a way to render the formula. Alright. Isospin. So I'm gonna copy link to page as well. Now I know what baryons are. Incredible. Okay. Alright. But what does that have to do with oxygen? Well, it really has very little to do with oxygen. So I am going to throw all that into particle physics. But now we are talking oxygen. Okay, oxygen. What are the properties of oxygen? Yeah, so part of it, a large part of it was on respiration. Okay, it was developed by, or discovered by Carl William Scheele in Uppsala, 1773 or earlier, and Joseph Priestley in Wiltshire in 1774. But Priestley published his work first. Dephilosigated air, which was coined by Antoine Lavoisier, who first recognized oxygen as a chemical element and correctly characterized it, its role in combustion. It's very useful. I mean, it's obviously very useful. Pneumatica. Pneumo here means like wind and stuff like that, or air. Philo of Byzantium. Okay. Leonardo da Vinci. J.J. Becker. Georg Ernst Stahl. It's very abundant in Earth's crust. Oxygen is the most abundant in Earth's crust, followed by silicon, aluminum, iron, calcium, sodium, magnesium, potassium, titanium, hydrogen, phosphorus, manganese, fluorine, barium, strontium, sulfur, carbon, zirconium, chlorine, vanadium, chromium, rubidium, nickel, zinc, cerium, copper, neodymium, lanthanum, yttrium, nitrogen, cobalt, scandium, lithium, niobium, gallium, lead, boron, thorium, praseodymium, samarium, gadolinium, diprosium, erbium, argon. Oh, there's argon in Earth's crust. That's crazy. Okay, the least abundant is At, or astatine, francium, promethium, radon. Radon is pretty common, actually. Well, in basements, which is where I am right now. Okay, oh boy. Alright. So it's mostly oxygen. It's mostly oxygen, silicon, aluminum, iron. Yeah. So this graph sort of does it all. Major metals are ranked by oxygen, silicon, aluminum, sodium. Yeah, okay. Sodium. It's very close, though. There's hydrogen, magnesium, potassium, calcium, iron, titanium, manganese, phosphorus, sulfur, chlorine, fluorine, and carbon, which is basically the top, like, 17 elements. And then these are like metals. So iron is very common. Titanium is really common. Magnesium, sodium, aluminum. Aluminum is very common. Silicon is very common. That's why we can make chips and have computers. Chromium is copper. Ni is nickel. And then there's zinc, mobium. Sn is tin. W is tungsten. And Pb is... Actually, I forgot what Pb is. Yeah, Pb is lead. Okay, whoops. Yeah. Okay, and then there's like rare metals or precious metals, like gold, platinum, palladium, other important stuff. Silver is also considerably precious, but like not as rare. Copper, on the other hand, is very common. And then there's like other stuff as well. Oh yeah, I think now it's like the amount of money it costs to make like copper currency is like less than the amount of denomination it holds. Going back to oxygen. So, okay, so a bunch of people know that oxygen is very strongly related to combustion because essentially combustion is just you're doing a lot of redox equations, right? You're doing a lot of redox reactions. Speaking of which, redox basically means like there's something that's being oxidated and stuff that's being reduced. So if you are oxidated, usually you gain electrons, and if you're reduced, you lose electrons. And the idea was really extracted from how things react with oxygen, because usually what happens is when you react with like oxygen, you switch like a part of like for example let's see, what's a good example. Like you might be like burning something, like say like you're burning glucose, right? Which, I mean, for all organic compounds, once you burn them, you get water and carbon dioxide. So you burn that, and you get a bunch of water and a bunch of carbon dioxide. So what happens for the hydrogen molecule is that it, in the previous case, since oxygen is negative, hydrogen, I think, plays a positive role there, and carbon is neutral. And the relationship is maintained in water. But for carbon dioxide, carbon used to be neutral. Now it has a +4 state, since it's CO2 and the O is negative. So carbon just gained like 4 electrons. So carbon was oxidated, and or no, carbon was reduced. Well, oxygen itself was the oxidant, or it oxidated like things. Okay, so oxygen is very useful in combustion, and it's the thing that causes combustion. But in the early experiments, people had philosophical ideas about the elements of the world, that is metal, wood, water, fire, and dirt. And so the fire part they associated oxygen with, but weren't really able to identify that. Then yeah, they did some experiments. Robert Boyle found that it's important, found that oxygen is important for respiration. There's also phlogiston theory. So a bunch of dudes, Robert Hooke, Olborch, Lomonosov, and Bayen, so they were able to produce oxygen, but they weren't able to identify it as an element. It was until Antoine Lavoisier in 1777 who realized that this was in fact an element, right? Well, it's commonly attributed that, okay, Scheele. Okay. Okay, so Lavoisier realized that air was stuff that you can breathe and you can use for combustion and other stuff. So later, the other stuff became nitrogen, which is the most abundant gas in our atmosphere. Okay, there's trioxygen or ozone. Sort of smelly. I think ozone means like smelly in Greek. It's produced in the upper atmosphere. Combines with atomic oxygen made by the splitting of UV radiation. So ozone absorbs a bunch of UV, and it's the planetary shield. Efficient atomic oxygen is corrosion of spacecraft. That's interesting. Metastable. Okay, so tetraoxygen is metastable. 6 phases of solid oxygen. Amazing. Gigapascal. Rhombohedral. O8 cluster. This cluster has the potential to be a much more powerful oxidizer and may therefore be used in rocket fuel. Okay. I think I sort of skipped this part. Okay. Physical properties, oxytocin stellar spin, currents analysis, production, role of O2. Okay, I've been doing this for like almost 80 minutes, so I might need to take a little break. Let me just check my stream real quick. Production, role of O2. Yeah, okay, cool. Yeah, alright, so I'm gonna turn on a screensaver instead. Okay, how do I turn on a screensaver? Alright, llamas, or sheep. Gotta love sheep. Okay, whoops. I'm gonna open image in new tab. Yeah, just look at sheep. Be sheep, guys. Be sheep. Okay, wow, they have weird stuff on their ears. That's weird. Okay, yeah, but be sheep. Alright. I'll be back. I am back. Okay. What is this? Okay, characteristics. Oh, the abundance of elements in the universe. Production. Buildup in the atmosphere. Industrial production. Important stuff. Okay, honestly, I sort of want to do some math now. So I'm gonna change this, math comp grind screen, learn random stuff about, math competition geometry. Yeah, I'll still use the whimsical, cover, but yeah, okay. So, okay, we can do some math here then. I'd been working through this set. Okay, whoops. I'd been working through these set of problems because I'm pretty bad at geo, and so I'm shooting for a USIMO qual this year, which is probably a lot harder because of the cheating scandal for AMC. Granted, I'm a senior now, and it doesn't really matter, but it'll always be nice to qualify for USIMO. So, to do that, I sort of need to get probably 12 questions on the AME. And so to do that, since it's usually it's usually 4-4 for algebra geo, and then maybe 4-3 or 2-2 and some mixed problems between discrete math and just miscellaneous stuff. So yeah, one thing I need to work on is I can usually constantly get all the algebra questions. I can get 2 or 3 of the geo questions, but I'm not that good for geo. I'm also pretty mediocre for combo, but I'm very good at number theory. So for algebra and NT, I can probably get 6 or 7 questions, or I can basically get all of them. So then if I can bump up my geo, I can probably get 11 or 12. So looking at these problems, okay, I don't know. Oh boy, I just saw the solution. Okay, but I can still do it anyway. Here, let me plug in my iPad so that I can just do it with my iPad instead of doing it with other stuff. Okay, that'll be fun. Yeah, okay, here, let me switch this over to my iPad. Okay, let's see. Alright, so I was working on. What was I working on? The video capture device. I'm gonna delete that. Delete that as well. Okay. Okay. No. And delete that. How do I show my iPad? Oh, am I supposed to like project this? I don't know. I don't think so. Image, video capture device. No, that's not how it works. How use iPad to OBS. Okay. Doesn't automatically connect. I have to use a plugin? What? Are you serious? Okay, I'm just gonna...
Next thing you're going to want to do is go to settings. You'll come here to video. You'll select the resolution that you want to film at. So I want to film everything at 4K. So I'm going to come here down to the scene area. And this is where you're going to click plus, the plus button right here. It's going to say enter the name of this created, but we don't have any sources. Here's food, which already said trust computer, and you'll come here to video capture device. We'll name it iPad.
Oh wait, what the heck? Okay, a video capture device. I have that. That means I didn't plug in my iPad properly. Ah, here we go. Okay. My iPad. Okay. Here, my face. My face is over here. My iPad. Can like that. And then to actually show which screen I'm doing, I'm just gonna add existing macOS screen capture. So for this, right, this is my macOS screen capture. What I want to do is I want to display the problem properly. Alright, I want to display the problem, but I also want to display my iPad. Okay, here. Alright. That's rather minuscule. There's probably a better way to render that. It is what it is. Let's stick with that. Okay. Okay, I did a bunch of suspicious stuff, but GeoGrind. Okay, I'm just gonna do some random math. Okay, this problem. Figure like that. 1/3 of their perspective sides. Okay. So yeah, also let me display the sides. BC, D, E, and F. There's N1, N2, N3. So, and then it looks somehow, okay, and converts the ratios into like 3:1. So, how do we tackle this problem? Well, first of all, what do we want? We want N1, N2, N3, right? So we want that and its relationship to ABC. Two ways I have off the top of my head. Since there's a lot of Cevians, I think the best way is just to use mass point, since it's very quick if you do it that way. So it's 1/3 of their respective sides. That means the weight for that would be like 2, 3, okay. So if I arbitrarily say that the weight of like say B is 1, then weight of C would be 2, right, since this is a 2-to-1 relationship. Okay, and this is 2, then weight of A would be 4. Okay, then the weight at D would be 3, the weight at E would be 6, and the weight at F would be 5. Does that make sense? Well, since that should be 3 to 4, but it's not, so that doesn't make sense. Okay. Alright. Yeah. I think it's a bit hard to assign masses in this diagram. Okay, well, the other way to do it is with barycentric coordinates. So if I say that A is 1, 0, 0, okay, here, let me use a green pencil. If I say that A is 1, 0, 0, B is 0, 0, 1, and C, okay, 0, 1, 0, and C is 0, 0, 1, then I can sort of easily populate the coordinates for D, E, and F. So E would be, since it's the 2/3 or third point, that means that'd be 2/3, 0, 1/3. Similarly, that would be 2/3, 1/3, 0. Right, and this would be what do you want to call it? This would be 2/3 or 1/3, 2/3, 0. Okay, so to find N2, that's 3 to 4, right? 3 to 4. So the split would be, think about it, it's closer to A, so that means 4/7, and then okay, wait, how do I split this? Means it's 3 7th times 1/3, 3/7 times 2/3, and so that gives you 4/7, 7th, 2/7. If you think about it, what you do when you go from A to D is you take 1 and you split that into 1/3 and 2/3, right? Then if you're only going 3/7 of that distance, you split 3/7 into 1/7 and 2/7, and yeah. So this is right. This is, I mean, it's just like applying like the midpoint formula in Cartesian coordinates. So that is the coordinates for n2. For n1, I think it's very similar. What you do is 4/7 here. It's just a permutation of n2, right? So 2/7, 1/7, and for n3, another permutation here. 4/7, that slot, 2/7, 1/7. Okay, so there's this interesting formula which says that the area of n1, n2, n3 is area of ABC times the determinant x1, y1, z1, x2, y2, z2, x3, y3, z3, where where x, y, z are the coordinates for each point respectively. So if you jot that down, you get 4/7 or 1/7, 2/7, 4/7. Also, the ordering doesn't matter at all. So 4/7, 1/7, 2/7, and 2/7, 4/7, 1/7. So I mean, 412 is yeah. So they are all odd terms, right? Then that's 1/7 cubed, 111, 444, 222, so 1 cubed plus 4 cubed plus 2 cubed, minus 246, 241, 241, 241, so 3 times 8, right? What is this? This is 64, this is 8, right? So minus 16, 48, 49. 49 over 7 cubed is just 1/7 squared, or 1/7. So that means that the area of n1, n2, n3 is 1/7 that of ABC, and the answer is 1/7, which I spoiled a while ago. So barycentric coordinates, just a crazy bash. Yeah. Okay, I'm gonna look at the solutions. Symmetry is very important, kids. I agree. I totally agree. Okay. Oh, he just bashed that. Okay. Oh, dang, yeah. Okay. You could also use PIE on this. Wait, let me see how you use PIE on this. Oh, so it's like, that's interesting. Since, yeah. Okay. I mean, I wouldn't think immediately to use like pi on this, but that's an interesting idea though. Like, let's try it out. So if I color this blue, if I color like, okay, so ABD, that yellow, and BCE. Okay. So what I want is the intersection, right? What I want is the intersection of 2 vertex and one random point. So you have 3 of these triangles. You have ABE, you have ACF, and you have BCE. Alright, and so the intersection of those 3 is what we want. Now we know from pi that the sum of the 3 areas, so the sum of 3 areas is what? If we say that the area of ABC without losing generality is 1, then the sum of the area, since this is 2/3, so that'd be 2/3 times 3, right? And that is equal to the area of of all of that union together, so it's 1 plus blue and yellow. What is blue and yellow? Blue and yellow is all that minus minus pink, right? Or no, what is blue and yellow? Blue and yellow is ACD, or AFD. So how do you calculate AFD? Well, that would be 2/3 times times 4/7, right? And similarly, if you do blue pink would also be similar. Yes, blue pink is similar. So you multiply that by 3 and you plus x. So 1 is equal to what? A over 7 plus x. Okay, x has to be negative 1/7. So there's some like weird rounding error here. I mean, maybe you should like, I don't know, plus the absolute value of x, I guess. So for some reason you have negative area. Oh, wait, wait. Since A, oh no. Oh yeah, no. Okay, so A union B union C is equal to A plus B plus C minus A intersect B minus B intersect C minus C intersect A plus A intersect B intersect C. So A union B union C is 1. A plus B plus C is 2. That is 4/7, or that's 2/3 times 4/7 times 3, and that is x. So what we want is 8/7 minus 1, which is 1/7, which is x. That is a lot faster than bashing with baryon-centric coordinates. But, I mean, if you can like somehow bash this with a coordinate system, you've already won the game. Because you know that a computer can also do that. Alright, next problem. Oh boy, okay. How do I not see the solutions? Okay. Alright, I feel like what I should do is I should organize this. How do I do that? I go to OneNote. I go to Math Olympiad. I go to this folder I was working in. Call this GeoGrind. Okay. And for this, I call, what do I call this? Okay, 1952-49. Okay. Now I add another one. What do I call that? 1960-32. Why do I want to organize it that way? I mean, it really doesn't matter, right? But I sort of want to keep track of what the problems I'm actually doing. Okay, now you got a circle here. Center of that is O. AB is perpendicular to BC. BC is the diameter. ADOE is a straight line, so that's 4 concurrent points. AP is equal to AD. And AB is twice the radius. Okay. And then there's a bunch of statements. So let's just look at that. So if I call the radius R, then okay, all of these are R. AD is equal to AP, if we call that X. And then PB is 2R minus X. Okay. Well, first of all, we can just use the Pythagorean theorem on triangle ABO because it's R and 2R. That means that AO is root 5R. That means X is root 5 minus 1 times R. Log R is 1. And X is root 5 minus 1. Okay, Now we want to consider the statements. Okay, number one, we've got AP squared is equal to PB times AB. Well, AP squared is just 6 minus 2 root 5. PB is 2 minus that, so 2r minus x, or 2 minus x is equal to 3 minus root 5. So 3 minus root 5 times 2. Okay, then this is correct. Well, since there's only one correct option, you can stop from there. But we are prepping for the AMY, and this is AMC style, so I will verify all the other options as well. AP times DO, so DO is 1. AP is root 5 minus 1. Is that equal to PB times AD? Well, PB is 3 minus root 5. AD is root 5 minus 1. So they're clearly not equal to each other. So no. AB squared, is that equal to AD times DE? No, because AB squared is equal to AE times D. It's equal to AD times AE by the whatchamacallit. The power of a circle theorems, since both of them are equal to the power of a point of the point A. So C is wrong. No. AB times AD is equal to OB times AO. Well, that's OB times AO is root 5. AB times AD is 6 minus 2 root 5. So that's no. So well, and none of these is clearly incorrect. So solution is A. Yep. Okay. Next one. 1960, 37. Oh, I've done this before. Okay, I'm going to skip that. 1961, 27. Oh boy, I do not want to see the answer. Okay, this is sort of obstructing our view as well, which is really boring. Oh yeah, maybe we can situate it that way. Oh, here we go. See? Uh-huh. Alright. So, given two equally angular polygons, P1 and P2, with different numbers of sides, each angle for of P1 is equal to, or is x degrees, and okay, P2 is x degrees. Okay. So I'll call this 1961, 27. Alright, you can see that P1 has N1 edges and P2 has N2 edges. Then number of, or then each angle of P1 is N1 minus 2 divided by, or times pi divided by N1. And then that is equal to k pi N2, and 2 minus 2 over N2. So this cancels out. So without losing generality, sub N1 is U and N2 as V. And so what happens in this case is we are really just solving for N1 and N2. Alright, but N1 is not equal to N2. Okay, so the question is for f of t is equal to t times t minus 2 over t. Will it ever happen that f of m is equal to kf of t, where k is an integer? Okay. Well, clearly f of m is not equal to f of t, but, for example, I can... I'm tempted to say that, like, there's infinite many pairs of solutions. Because this is equal to x. So for each valid n1, there's always an x. All right. So oh yeah, no. Also, there's no n1 here. Okay. You know what? I'm just gonna solve that. So u minus 2 over u is equal to v minus 2 over vk multiplied by uv on both sides. uv minus 2v is equal to kuv minus 2ku. That means 2k u minus v is equal to uvk minus 1. We are solving for k. Actually, if we solve for k, then we should do k is equal to u minus 2v over uv minus 2. Okay, and we want k to be an integer. Probably a positive integer. That means... Okay. And possibly larger. Okay. So that means u has to be greater than v. If u is greater than v, well, I think it's constructible. I'm also not sure why this is taking so long. 2 over u, 1. No. Okay. Oh, hold up. New idea. Okay, if I rewrite this as right, since it's 180 n minus 2 over n is 180 minus 360 over n, yeah. Okay, so x is equal to 180 minus 360 over n, or over u, and kx is equal to 180 minus 360 over v, so 360k over u is equal to 180 minus 360 over v. Divide by 180, you get 1 minus 2k over u is equal to 1 minus 2 over v. Okay. So then k is equal to 1 minus 2v over 1 minus 2u. And I think it's infinite. Just have to, okay. Nope. Not even close. Okay. All right. Let's look at the solutions. Okay. K is 2. Acute angle. What? Okay. They approach 180. Means kx is less than 180. X is less than that. There are no values of x that satisfy this equation. What? Angular quadrilateral. Oh, okay, yeah. Whoops. Okay. So, nope. That is... Here's the idea. Okay, so this was the right direction, alright? So if the angle for this equiangular polygon was x degrees, then its external angle would be 180 minus x. And that is equal to 360 over n. Right? Now, the thing is, that means x is equal to 180 minus 360 over n. That means x is less than 180 degrees. But since kx is also the angle for an equiangular polygon, that means kx also has to be less than 180. Right? Plus, since it's an equiangular polygon, it has to have the angles of a perfect polygon. So that has to be 60 degrees, 90 degrees, 108 degrees, 120 degrees, yada yada yada. So if k were equal to 2, x has to be less than 90 degrees, x is 60 is the only valid solution. But if k is 3, x is less than 60 degrees, and there's no sol. So x is 60 is the only solution. Okay. Alright, there